So this afternoon, I'm going to talk about the very early history of the idea of having a machine or a robot or AI that could reproduce and evolve just like biological organisms do. The talk is going to be based upon a book that Alan and I co-authored and was published last year by Springer called Rise of the Self-Replicators. So you can find this on the Springer website if you have access to that through your university library. And there's also a free author formatted PDF version on my website here. So to start with, I should say, why am I so interested about self-replicating machines that I wanted to write a book about it? Well, right back to my PhD days in the 1990s, I've been interested in self-replicating agents. It's always seemed to me that having self-replication rather than a more traditional evolutionary algorithm approach where you have a fitness function, so you have a particular target that you're aiming towards. If organisms and agents can reproduce by themselves, then that seems to create a much more open-ended dynamic and possibility for open-ended creativity, more of the sort that we see in the biological world. When you get into studying the details of self-replication, you soon get deeply involved in questions of autonomy and agency. And using self-replicating systems in software and in hardware can be used to experimentally address questions concerning definitions of life and the origin of life. And then, of course, there's massive economic implications of having a technology that can increase its production at an exponential rate and could potentially be used to do useful things as well as self-replicate. Just out of interest, I recently came across this company, Foundation.si, which is a new startup company currently closing a round of seed funding. And they say, we are building the first factory on the moon. Our vision is to develop infrastructure in space with self-replicating robots. I spoke to one of the co-founders, Justin. Actually, turns out that the two co-founders met when they were at the University of Edinburgh, just down the road from me. Okay, so there's certainly still interest in this area now as much as there ever has been. If you look back at books on the history of self-replicating machines, and there are some good ones, in particular, Kinematic Self-Replicating Machines, a book written by Robert Freitas and Ralph Merkel in 2004. There are also some nice review articles, such as this one, 50 Years of Research on Self-Replication by Moshe Siba in the Artificial Life Journal. Both of those have nice genealogies of work in self-replication, showing how it's been mapped out over time. But you'll notice from both of these that they start with John von Neumann in the late 40s and early 1950s. So I wondered, what came before John von Neumann? Did he have all of these ideas by himself out of the blue? Or was there other preceding work upon which his ideas were based? Both of these reviews allude to bits and pieces of earlier work, but really this pre-1950s development of the idea is uncharted territory. And that's the reason I wanted to write the book, to map out more fully what had happened before the 1950s. So why am I interested in the early history of self-replicating machines? Well, as I've suggested, it actually has a very long idea, much longer than you might expect. These seem like very modern ideas, but in fact, they go back several hundred years. And so this long history of ideas represents a rich resource of ideas, suggestions, visions that are still relevant today. And in fact, as technology develops, they're probably more relevant today than, say, they were when, a piece was being written 150 years ago. A lot of what I'm going to talk about is literary work rather than scientific or engineering. And there are some benefits to that. Literary writers are not confined to the limits of the day's technology, and so they tend to let their imaginations run wild and look further into the future. And as I'll demonstrate throughout the talk, I think there are some advantages of looking back on what has happened in the literary world, as well as the scientific and engineering areas. Okay, so in our book, we traced the idea of a machine that could reproduce back to René Descartes' time in the 1600s, and really the aftermath of his suggestion that animals could be considered as natural automata. That is, their workings could be explained purely in physical terms. And that notion already has the idea inherent within it, that of a self-reproducing machine. If animals are machines, animals reproduce, therefore machines can reproduce. Descartes never actually put it in those terms, but we don't have to wait too long until we find people who do talk explicitly about the idea of a machine that might be able to reproduce. But things really hot up around the 1850s. And this is where I'm going to concentrate on in this talk. There are two reasons for this acceleration of ideas in the 1850s. One was it comes hot on the heels of the climax of the British Industrial Revolution. So in the early 1800s, people were already looking at the machines around them in factories and seeing them becoming more and more complicated, wondering where this trend might eventually take them. There's a novel written in 1844 by Benjamin Disraeli, who went on to become the British Prime Minister. He was also an author. He wrote this novel, Coningsby, and there's a passage in that where the narrator is surveying the industrial landscape of Manchester. And he has this passage, and why should one say that the machine does not live? It breathes, it moves, and has it not a voice? And yet the mystery of mysteries is to view machines making machines, a spectacle that fills the mind with curious and even awful speculation. So even back then in the 1840s, people were clearly concerned about what the long-term trends of this increasing complexification of machines might mean for humanity. The second factor that really ignited ideas in the 1850s was, of course, the publication of Darwin's On the Origin of Species in 1859. The very next year, the American botanist, friend of Charles Darwin, Asa Gray, published a series of articles in the Atlantic magazine, where he tried to popularize Darwin's ideas. And there's a piece in here in these pieces that I think is the first example where there's an explicit analogy drawn between the process of biological evolution and the evolution of human technology. So Gray says, man alters from time to time his instruments or machines as new circumstances or conditions may require and his wit suggest. Minor alterations and improvements he adds to the machine he possesses. He adapts a new rig or a new rudder to an old boat. This answers to variation. In course of time, the old ones would be worn out or wrecked. The best sorts would be chosen for each particular use and further improved upon. And so the primordial boat be developed into the scow, the skiff, the sloop, and other species of watercraft. This is natural selection. Of course, in this passage, Gray isn't explicitly talking about self-reproducing machines, but we don't have to wait long at all until we see people explicitly talking about the evolution of self-reproducing machines. This is a little map of what I will talk about in the bulk of this talk, and I'm going to divide this into 4 categories. The first will be early literary work from the 1860s to the 1920s. Then I'll talk a bit about early sci-fi stories, especially pulp sci-fi from the 1920s to 1950s. I'll say a bit about scientists speculating about self-replication and evolution from the 1920s onwards. And then finally about the development of theory and implementation of self-replicating machines in science and engineering disciplines. So let's look at the first of these, the early literary work from the 1860s onwards. The first person I want to talk about is Samuel Butler. He was an English author. He emigrated as a young man to New Zealand in 1859. He was wanting to get some independence from his family, maybe generate his own wealth by setting up a sheep farm in New Zealand. There was some connection, family connection between the Butler family and the Darwin family from a while back. Butler had read On the Origin of Species soon after he arrived in New Zealand. This inspired many of his later written works, including a letter written to a newspaper, which I'm about to talk about, Darwin Among the Machines in 1863, various other letters, and then probably his most famous novel Erewhon, which was published in 1872. So this is the front cover of the Press newspaper, a local newspaper in Christchurch, New Zealand. We can see the date, Saturday, June 13th, 1863. Here at the bottom of the second column, it's a start of Butler's letter, Darwin Among the Machines. So Butler remarked that it is true that machinery is even at this present time employed in begetting machinery, in becoming the parents of machines. So this is the idea that Disraeli had commented on 20 years previously. But he went further. The reproductive organs of the machines might become developed in a manner which we are hardly yet able to conceive. So he saw this process continuing, machines getting less and less reliant on humans to maintain themselves and to build more copies of themselves. And it might reach a stage where humans are completely redundant and the machines literally become self-replicating. In Butler's various works, he had various different ideas and sort of changed his views a bit on where this might lead us. But it's fair to say in most of his lines of thought, it didn't really work out very well for humankind. Butler wasn't the only person talking about this sort of thing at this time. I'll talk about one more example, which is George Eliot, the pen name for the British author Mary Ann Evans. In her last published work, which was called Impressions of Theophrastus Such in 1879, she had a chapter, it's the second last chapter of the book, called Shadows of the Coming Race. And this chapter was about two characters, one who was quite enthusiastic about mechanization. The other one was a bit more cautious about it. They were wondering how things might develop. There's this wonderful passage at the end of this chapter where one of the characters says, thinking of the time where machines might be able to produce themselves, many of the ideas that Butler had also covered. And because they were, as this character said, uninhibited by such petty things as consciousness or emotion, he reckoned that they would outperform humans and eventually supplant us as the dominant intelligent species on Earth. And so he says, thus this planet may be filled with beings who will be blind and deaf as the inmost rock, yet will execute changes as delicate and complicated as those of human language and all the intricate web of what we call its effects, without sensitive impression and without sensitive impulse. There may be, let us say, mute orations, mute rhapsodies, mute discussions, and no consciousness there, even to enjoy the silence. So it's a pretty dystopian view that's being set out there. George Eliot, Samuel Butler, there was also Alfred Marshall, who I've not spoken about, all at that time talking about very similar things. I tried to map out the relationships between all of these people to try and figure out what the exchange of ideas was. As you can see, it's a pretty tangled mess of personal and professional relationships. In fact, Eliot says at the end of her chapter that these ideas seem to be flying around in the air with other germs. This is a theme that comes up several times in this story, and also in other areas of science. It's quite common that there are periods of time where there are ideas that seem to be floating in the air. All of the components required for those ideas are established, and various people link them together in the same way at the same time. And it seems to be maybe some element of collusion going on, but in fact, they're all independently coming up with the same idea. The final character I want to mention in this section on early literary work is our friend Karol Čapek in RUR. So in that play, the robots were collectively and collaboratively building their own offspring. So they were working in the factory to produce more of themselves. This suggests or highlights the fact that there may be different kinds of architecture for self-replication. It doesn't have to be a monolithic, like single robot that's building a copy of itself, but it could be a collaborative endeavor by a collection of robots, each of which is doing a specialized function, but between them all, they can perform all of the tasks that are required to build more of themselves. The climax in the play could be seen as a struggle for the ownership of the robot's DNA, as it were. So the only thing the robots can't do is they don't have access to the secret chemical formula that is constitutes the living matter from which they are made. And so at the end of the play, there's a struggle for these written instructions, which are hidden in Rossum's safe. This is just to demonstrate by looking back at these old stories, it suggests new things that we tend to get funneled into one way of thinking about how a task can be achieved. But whereas in fact, sometimes there are other solutions which are just as plausible. Okay, so the second branch of work I wanted to talk about is early science fiction stories, particularly early pulp sci-fi, which was born in the 1920s in America. So these are mass-produced, cheap short stories that are published on a regular basis. And from the 1920s to the 1950s and onwards, from there are just loads and loads of stories that talk about machine self-replication and evolution and how that might turn out. These are just a small selection of my favorite ones. I'll just talk about one or two of these. The first example that I've found of a story involving self-replication and evolution is this short story Automata by the British author S. Fowler Wright, published in the magazine Weird Tales in 1929. Now, the structure of this story, I'll just set out because it's quite similar. There's certainly many of the themes here are covered in many of the other sci-fi stories and the other literary work which I've already spoken about. So at the beginning, this is recognition that humans are becoming more and more servants of machines and tending to the machine's needs. And that there's a process by which the machines are becoming less and less reliant on humans to do this. And at some point, if you extrapolate into the future, they may become completely independent and able to reproduce by themselves. There's also a notion in Automata of machines designing their own offspring. Now that's an interesting point. Again, I don't think there's really been much substantive work on this issue of machines designing their own offspring in recent AI and artificial life. It's a topic that's talked about a lot in the AGI literature, but I don't think there's been a lot of concrete progress in that area. So these stories generally look at how this might work out for humans. A lot of them end in the human race going extinct. And a lot of them talk about this question, is this the inevitable next stage of evolution? And if so, is that a good thing or a bad thing? Some people view it as a bad thing. Obviously, the end of the human race, probably not good. But on the other hand, some people look at it as something to be proud of. And rather than being replaced by some random other biological species, that humankind might actually perpetuate itself by creating its own successor that will carry on in some form or other the flame of humanity into the future. And then going back, a lot of these stories ask, what can we do to avoid this fate? And the common response is, we must destroy all machines now and have nothing to do with machinery. Go back to a simpler way of life. This is actually, this was a topic that came up in Butler's Darwin Among the Machines in 1863. But even then, for Butler in 1863, he said, well, yes, we could do that, but let's be honest, we already rely far too much on technology, and it's completely inconceivable that we would be able to give it all up now and go back to a simpler life. He wrote that in 1863, and if that was true then, it's true a million times over now. So there's this nice passage at the end of Automata. Even in the early days of the 20th century, man had stood in silent adoration around the machines that had self-produced a newspaper or a needle. And at that time, they could no more have conceived what was to follow than the first ape that drew the sheltering branches together could foresee the dim magnificence of a cathedral dome. So there's this sense that we are playing with technology, that we don't understand what the long-term implications will be for us, for the future of mankind. There's one more sci-fi story that I'd just like to mention quickly. This is a story called Crabs on the Island, give it the English title, by the Russian sci-fi author and science popularizer Anatoly Neprov. So this story involved an inventor and his colleague traveling to a remote island. When they get there, the inventor unpacks a whole load of boxes, one of which contains this little, what looks like a toy crab. Turns out to be far from a toy, and the narrator or the inventor explains that it can build a copy of itself, it can self-produce, and he's brought it to the island along with a whole load of junk metal for it to use as food, to test Darwin's theories of evolution. Sure enough, this crab starts reproducing, and before they know it, it's entered a vicious arms race, all these evolving crabs. They get bigger and more ferocious. And suffice it to say, it doesn't end well for the inventor when one of these vicious crabs notices that he's got a crown in his teeth and thinks, oh, that will be a nice bit of metal that I can use to reproduce myself. Neprov was an interesting guy. He had interest in artificial life and artificial intelligence. He also wrote a short story called The Game in 1961, which addressed topics of whether machines could think and really understand things. And the story involved a set of humans just following instructions to translate messages from Portuguese to Russian. That might sound like a very familiar story. In fact, it's pretty much the same as John Searle's Chinese room argument, which was published 20 years later. So yeah, Neprov is certainly a very interesting guy, and I would like to know more about what he's done. So moving onto the third part of our story, the development of speculation from scientists about self-reproduction. First significant person to talk about is J.D. Bernal. He was a British X-ray crystallographer. In fact, two of his PhD students went on to win Nobel Prizes, Dorothy Hodgkin and Max Perutz. Bernal was also very interested in the relationship between science and society, and he had a wide range of interests and published on a wide variety of topics. One of the first things that he wrote about was this short book called The World, the Flesh and the Devil in 1929. This was an attempt to look into the very far future of humanity and to discuss what you might be able to say about that from a scientifically defensible point of view, avoiding obvious pitfalls. Arthur C. Clarke later referred to this book as the most brilliant attempt at scientific prediction ever made. So Bernal noticed that, well, he realized that there would inevitably come a time in the future where humans had run out of resources on Earth. And if the human race wanted to continue to expand, they would be forced to move into space and to think about colonizing other planets. So he wondered about how that might come about, and he had this vision of, first of all, we might build these massive spaceships, globes, space globes, which would act as miniature planets. So he had this idea of a globe which would be about 10 miles in diameter, might be home to 10,000 people. And it would be a completely self-sustaining system. It would collect energy from the sun, it would collect materials from asteroids, and it would recycle everything inside to basically be an artificial world for humans to live in. But he said a globe which was merely a satisfactory way of continuing life indefinitely would barely be more than a reproduction of terrestrial conditions in a more restricted sphere. And so the essential positive activity of the globe or colony would be in the development, growth, and reproduction of the globe. So he saw these globes, one of their main functions would be to build other globes. And then that would allow the colony on that globe to expand to the offspring. And then he saw as these globes started reproducing, there would come a time where there was competition and some would be forced to find other sources of energy, so other solar systems. And that in the long term, this might be a mechanism where over many generations of living on the globes, humans might travel to other planets. And so here we get this notion of self-replicating machines being used as a mechanism by which humankind can travel to other planets. One more work of scientific speculation I'd like to talk about is by Andrei Kolmogorov. Many of you here will be familiar with Kolmogorov in terms of his work on definitions of complexity and information theory. But in the early 60s, Kolmogorov was very interested in questions about AI and artificial life and how that fitted in with society, particularly Marxist Soviet society. In 1961, he gave a talk at Moscow State University that was so popular, in fact, it had to be moved to a bigger lecture hall to accommodate everyone. The talk was called Automata and Life, and in the following year, he did two subsequent seminars on the same topic or similar topics. They were called Life and Thinking as Special Forms of the Existence of Matter and Cybernetics in the Study of Life and Thinking. So Kolmogorov noted that the age of space travel and the development of the computer both brought with them the pressing need to understand both life and intelligence from more generic principles, like so more general principles rather than being too colloquial about what's happened specifically here on Earth. So he started his lecture with these three questions. This is a translation by the US government, who like to translate a lot of these things. Can machines reproduce their kind? And in the course of such self-reproduction, can progressive evolution take place, leading to the creation of machines of a higher degree of perfection than the originals? Can machines experience emotions? And can machines have desires? And can they pose for themselves new problems not put to them by their constructors? So this was a public lecture, and Kolmogorov didn't go into too many technical responses to these questions in these talks. But he did say that as far-fetched as they seem, there's no fundamental argument against a positive answer to these questions if you take a materialist worldview. However, he did caution that to build artificial living systems that are really deserving of that name, you need to understand not just their functional performance, inputs and outputs, but their internal desires. This links into bigger question of how cybernetics and AI was accepted into Soviet Russia in the 1950s and 60s, and goes is connected to the Marxist view and celebration of the creative act of human beings, and also of thinking as a social activity. So there's a very interesting history that is waiting to be written about the early developments of AI in Soviet Russia, and I'm certainly not qualified to write that, but I look forward to reading it when someone does. Right, the final aspect that I want to talk about is from the late 40s, early 50s, we finally reach a point where we see the development of theory and implementations of self-replicating machines by scientists and engineers. As I said right in the beginning with these genealogies, John von Neumann in the 1940s and 50s really put the subject on a firm theoretical grounding. So he showed it was logically possible to build a machine that was fed instructions that directed it to build a copy of itself. And you could do so without any infinite regress of the information, having to have information about the offspring and then the offspring's offspring and all of that. So he showed you can do that without those problems. And not only that, you could also construct a machine that could build something more complicated than itself, which is contrary to general experience of how machines work. So his approach was, of course, inspired by Turing's idea of a universal computer. So von Neumann adapted that so that it was a machine that was acting upon the same kinds of elements from which it itself was constructed. And so when fed instructions, it could build an arbitrary machine according to those instructions. And because of this universal nature, if it was fed instructions of how to build itself, it could build a copy of itself. So this really introduces the idea of self-replicators as maker replicators, where they can make anything as well as reproduce themselves, and could be possibly directed to make things that would be valuable to us. These ideas were explored a bit more in a paper called Artificial Living Plants by Edward F. Moore, published in Scientific American 1956, where he discussed what it would take to have a von Neumann style maker replicator in the real world, which would be powered by sunlight, using resources around it in the environment to reproduce itself, and which could be directed to produce valuable resources, materials, energy for humans, which we would then harvest. He discussed a little bit about potential dangers and environmental hazards which could be involved in this, but it's fair to say he didn't discuss those at very great length, and there's certainly a lot more that should be done to address those problems. So we finally see the first implementations of self-reproducing machines, both in software and in hardware in the 1950s. I should say that both of these take a much simpler view of self-reproduction. So they didn't implement anything like von Neumann's universal constructor approach, but they had a much simpler system of linear chains, inspired a bit like how DNA is reproduced by template reproduction. So Niels Baricelli, who was working in von Neumann's group at Princeton in 1953, developed what was essentially a 1D cellular automata. And he saw patterns in this system which reproduced from one time step to the next and also evolved. He developed this in a series of publications over the coming decades. And then in hardware, similarly, in 1957, the British psychiatrist Lionel Penrose constructed this wonderful series of wooden models of self-replicating machines. There's some nice videos of this which are available on my website. generally, Penrose was interested in a whole load of different subjects, and he was very keen on building models, physical models, which he found a good way to test his ideas and assumptions of how something worked. I'm just going to show you a quick clip of one of these, just to give you a flavor of
limitations in size and the amount of information that can be carried are avoided by these molecules. They again can't link unless activated. They can be built into self-replicating chains of any given length. A seed of 2 connected units replicates itself, and a chain of 3 builds another. We can use more than one type of unit. Here is a chain of 2 blues replicating. Using both red and blue units, like always pairs with like, so that the new chain formed is exactly like the old one. Not until the final unit is in place on the new chain can the last cross-link holding old and new together be released.
There we go. Some really ingenious stuff. And this caused or attracted a lot of interest, not just in the scientific community, but also in on television, popular science programs. Penrose even set up a company to manufacture these replicators and sell them to universities and schools. It got a lot of attention in the press as well. Okay, so very nice work there. This is the final person I want to talk about today, Konrad Zuse, and I wanted to talk a bit about him because he's really very unknown in the artificial intelligence literature. So Zuse was one of the early pioneers of computers. If you look at his history, he's often described as the creator of the first digital computer. And these things always have asterisks by them. So there's always there's a hotly contested title, who built the first computer, and depends exactly what you call a computer, but he was certainly there in the early 40s as one of the pioneers of digital computers. But a bit later in his career, he was receiving an honorary doctorate from the Technical University of Berlin in 1957, and he gave a talk there, which was later published as a paper, called Thoughts on Automation and the Problem of the Technical Germ Cell. So what's his technical germ cell? He had this idea, or his problem was thinking about the practical issues and the practical applications of self-replication. So in particular, if you had a manufacturing plant, so you wanted to build, to construct something, could you generate that manufacturing plant from a simpler self-replicating system that could, with its maker-replicator abilities, create this whole manufacturing plant? And if you could do that, what's the simplest kind of germ cell, as he called it, you could construct? Simplest in terms of organization and function, that would generate this specific manufacturing plant as its output, maybe after a few iterations of reproduction. So this was the concept of the technical germ cell. And he went one further than that. He also asked, in terms of not just organizational complexity and functional complexity, what about the spatial complexity? What's the smallest spatial size you could get this technical germ cell to be? He envisaged this process of having a germ cell reproduce a copy of itself at a slightly smaller scale, and then a sequence of such operations. So you get smaller and smaller germ cells, to get to what he called the real germ cell. Now, he was well aware of the various technical problems that would be involved in that, and also the fact that you would need to switch to different physical principles of manufacture as you got smaller and smaller. Nevertheless, it was an idea that he thought we should consider for the long-term future. He also introduced in his work in this and later work in the 60s and 70s the concept of Raman, which is the German framework in which a self-reproducing machine operates. So something I've not really emphasized before, but a lot of people working in this area recognize that there's no such thing as a completely self-replicating machine. It always relies on some aspect of the environment in which it lives. And so the question is, how much and what specific features of the environment does a machine rely upon? And so this is a useful concept to bear in mind when discussing self-replication. In his work in the 70s or 60s and 70s, he actually started to design a part of his self-replicating machine, which was a general assembly unit. And his approach was to build everything out of a small set of modular parts to simplify the design. Seuss's idea of the technical germ cell brings to mind a sci-fi story that was published 2 years earlier by Philip K. Dick called Autophac. Now, in that story, it ended with a vision of a self-replicating machine generating these little seeds which were sent out into space, which would then land on other planets and start generating new self-replicating factories on other planets. So I wondered if there was any connection between Seuss's ideas. Had he read Dick's story 2 years before? It turns out, again, this was a completely independent idea. I came across these notes from Seuss from wartime, 1941. These are stenographics, so German shorthand. They were translated into German on the Seuss Internet Archive, and I translated them into English. And yeah, sure enough, he basically sets out this idea of a technical germ cell in 1941. So certainly before Philip K. Dick, and also before, way before von Neumann published anything. So again, Konrad Seuss is another person that probably deserves a lot more attention in the artificial life literature. Okay, so that's all I wanted to talk about in terms of the early history. As I say, the purpose of the book was to fill in the early history up to around the 1950s. Since then, of course, there's been a huge range of development that's well described in other books like the ones I mentioned at the start. Just picking out a very few highlights, NASA did a study of self-replication technology for space missions in 1980. There have been a variety of safety guidelines published in recent years, the earliest of which was probably the Foresight guidelines, which published its first iteration in 2000. So guidelines for the responsible development of nanotechnology, and there's a lot in there about what you should or shouldn't do when developing self-replicating mechanisms. And there's continuing work even today. There's the company I spoke about earlier, but then there's a lot of work on continuing the notion of self-replication in software and in hardware. In hardware, there's a lot of stuff about continued applications in space and concentrating on this idea of how you could build everything in situ and get all the materials you need in situ. So there's a lot still going on. Some final reflections. It's interesting to categorize this work that I've talked about. While they certainly have different goals and different types of issues raised, certainly from a sociological perspective, especially the literary work, has this question of takeover by AI versus a means for the continuation of humankind, certainly reflects the concerns of humanity for its relationship with machines. Some of the work has scientific goals, experimental study of living organization or the origin of life, and some of it has commercial goals, as I've set out. There are different analogies, as I mentioned. So von Neumann started with a machine analogy, sort of complex maker replicators, whereas others started with a much simpler origin of life analogy, starting with simple template replicators. And which one's appropriate, whether there may be something in between those, very much depends upon the goals of a particular research project. Their assumptions and context, analogies and perspectives shape the way that research develops. Sometimes we can take biological analogies too literally and be blind to other possibilities. So this idea of collective reproduction versus monolithic design Lamarckian evolution, direct transfer of learned knowledge, self-designing machines, and recursive self-improvement. There are technical and safety challenges. So the issue of production closure, where like Rotham's universal machines, everything within the factory being able to produce at least one part so that collectively they can produce everything that's required to make copies. Material closure, being able to get all the parts they need to reproduce, recycling of waste, balance of work between machine and its environment, the Raman, and mutations and the control of evolution. So open-ended evolution versus control of specific tasks, and the problem of value alignment. So if we allow these things to evolve, how do we know that they're going to continue to evolve, doing useful things and things that we might want them to do? And finally, of course, there's been a lot more development, as I mentioned, in terms of AI safety, as well as the foresight guidelines. There's the Leverhulme Center for the Future of Intelligence, Future of Life Institute, published the Asiloma AI Principles, Future of Humanity Institute, Center for the Study of Existential Risk, Machine Intelligence Research Institute, and many, many more. I don't have time to list them all. So I just want to finish with a quote from the final pages of our book. So whether this technology is ultimately beneficial or detrimental to us depends upon how well we understand the issues at stake and upon how that understanding enables us to properly manage its development. A thorough understanding of these issues should be based upon a sound appreciation of the history of the ideas involved. And so it's my hope that our book and this talk has had some little contribution to that goal of providing a sound appreciation of the history of the ideas involved. Okay, that's it. Thank you very much.